Serious developers will tell you to always favor composition over inheritance.
I don't even know what that means.
No one knows what it means, but it's provocative.
No, it's not. It's
Gets
gross.
the people going.
I mean, sure, you probably heard all the inheritance pain points. Tight coupling, complicated nested hierarchies, and an overall inflexibility that leads to difficulties in maintenance. But what does this mean in practice? Imagine that with inheritance, if you want to build a truck, you would need to build a car and a van first. With composition, you take all the building blocks from the engine to the wheels and compose them into the final truck. It is important to understand the pitfalls of inheritance in practice, so let's look at some code examples and see what are the alternatives to build more reliable software moving forward. We'll start by looking at inheritance in Kotlin, since Kotlin, and especially Java, are known for the hardcore use of OOP principles. Then, we'll spend some time looking at the benefits offered by Go, which encourages composition over inheritance. One of the big challenges in software development is code reusability. In OOP languages, this is solved through inheritance, where subclasses are extending the state and behavior of parent classes. Quick side note, this is known as class-based inheritance. In languages like JavaScript, objects can inherit directly from other objects in a more flexible process called prototype-based inheritance. So let's imagine we have to build a small app that allows people to draw shapes on a canvas. By the way, you are watching The Snippet, the series where we are analyzing code snippets from various programming languages to better understand useful software concepts. Since quite a lot of our code is duplicated, we naturally decide to extract it in a base class called shape. It all looks great on paper, but there is a major caveat. Sooner or later, a new requirement will come in and we'll be asked to add support for more shapes. Let's take them one by one. The circle doesn't have neither a width nor a height, so these properties are completely useless here. There are two options. We either put the width and height back in the subclasses, or we decide we don't really care and we store all the dimensions in the base class. Since option 2 already starts to look like we are building a God class, which is a pretty terrible anti-pattern, let's go with option 1. This is the new structure, but here is the kicker. The line shape introduces two new problems. Lines don't have an area, so the contract imposed by the shape class doesn't apply in this scenario. And lines can be drawn at an angle. But when you think about it, squares and rectangles can also be drawn at an angle, while this doesn't apply for circles. So we either put the angle property in the base class, and circle will have a dead property, or we put it in the child classes, and then wonder why the hell are we inheriting from the shape in the first place. And guess what? A new requirement just came in saying that some of the shapes should be clickable. Of course, we'll use an interface to define a behavior contract, but then we are faced with the same type of dilemmas. Since only some types of shapes can be clickable, who should implement the contract, the base or the child classes? I honestly don't know what the best answer is here, because it all depends on future requirements and various other constraints. You'll even find people suggesting that a new clickable shape base class should be defined, which leads to yet another set of problems caused by complex inheritance chains. Not to mention, we are lucky enough that Kotlin doesn't support multiple inheritance, which is associated with the notorious diamond problem issue. So let's switch gears to Go, which doesn't support traditional inheritance or classes at all, in an attempt to create a simpler, more maintainable system for code reusability. These limitations might feel weird at first, especially if your background is in a strong OOP language like Java or C++. However, you'll soon realize that these missing components are actually a blessing in disguise. We can use structures to group data together, methods with receivers to add behavior to that data, interfaces to define behavior contracts, and embeddings to compose types. Note that compared to Kotlin, in Go we don't need to declare that types implement interfaces. The association is implicit as long as the type defines the method required by an interface. This helps with decoupling and modularity, since the two entities don't need to know about each other. Back to composition, we can now identify the building blocks for our various shapes and compose them together in order to build the entity we need. We'll call the type that is embedded an inner type of the new outer type. There is one important aspect here. Through a process called inner type promotion, identifiers from the inner type are promoted up to the outer type. These promoted identifiers become part of the outer type, so you can access them directly in your code. So, while in classical inheritance, entities are built from parent entities through a direct relationship, with composition, entities are formed from independent building blocks through a more flexible and scalable process. Note that composition is not a one-size-fits-all solution, and that inheritance isn't always bad. However, understanding its limitations helps build cleaner, more modular and maintainable software. If you feel like you learned something, you'll probably find some of these videos interesting as well. Until next time, thank you for watching.